Welcome to the channel.
Welcome to this explainer. Today we're doing something a little bit different. We are going to completely forget about the sci-fi movies for a minute, and instead, we're going to demystify the actual, rigorous science behind gravity control and advanced aerospace propulsion.
What if we could just turn off gravity? I know, it's a question that feels like it was ripped straight out of a comic book, right? But today, we aren't looking at fiction. We are diving into heavily documented, real-world engineering inquiries pulled directly from a Defense Intelligence Agency report, alongside internal R&D from a massive aerospace corporation. We're going to see exactly how real physicists and engineers try to tackle the impossible.
So, here's our game plan for today. We're going to tackle the massive headache of modern aerospace, dive into some mind-bending relativistic and quantum physics, and then wrap it all up with the gritty engineering reality of BAE's Project Greenglow. Let's get right into it. Okay, part 1. The absolute bane of aerospace, the sheer, staggering cost of escaping Earth. Why exactly is gravity considered the ultimate enemy of transportation?
To really grasp the scale of this problem, we just need to run the numbers. Thanks to the rocket equation, a single-stage rocket actually has to be made up of over 93% fuel. 93%! And that's just to break free from Earth's pull. It's literally like packing your car for a big cross-country road trip, but taking up 93% of the interior space with just the gas tank. You are left with precious little room for the actual payload, the astronauts, or, the important science gear.
The whole issue boils down to this. Right now, we are entirely stuck using passive control. Basically, we just detonate massive amounts of chemical energy to violently fight gravity and shove a vehicle off the ground. But active control, actually levitating by directly nullifying the gravitational field, that would completely flip aerospace on its head. It eliminates the need for those giant fuel tanks altogether, letting us focus our propulsion strictly on moving from point A to point B, rather than just wrestling with the Earth's pull.
Which brings us to part 2, beating gravity by actually bending space-time with relativity.
So Einstein's general theory of relativity tells us that a moving mass actually creates a totally unique kind of field. Think about how a moving electric charge creates a magnetic field. Well, a spinning mass creates what we call a gravitomagnetic field. Theoretically, if you take a massive amount of matter and run it through a loop, you can induce a lens-theoring field. It's kind of like stirring a giant cup of coffee, except you're stirring space-time itself to create a localized upward push against Earth's gravity.
But, and this is a really big but, the catch here is the sheer scale of it all. Physicist Robert Ford actually crunched the numbers to see what it would take to generate just a standard 1G upward anti-gravity field using these forces. Get this, you would need to accelerate matter with the density of a dwarf star. We're talking about material where a single teaspoon weighs thousands of tons, and you'd have to pump it through pipes as wide as a football field, wrapped around a kilometer-wide donut. So yeah, the math works out beautifully, but the mass requirement is practically impossible.
There is another relativistic approach, though, and it uses exotic matter, specifically negative energy. General relativity actually suggests that negative energy density acts like gravitational repulsion. So picture wrapping a whole spacecraft in a bubble of this negative energy to just effortlessly float away. Sounds amazing, right? Except any realistic thickness for that bubble wall would require negative energy densities equal to a neutron star. Once again, pure physics says yes, absolutely. Reality says good luck with that.
All right, part 3. If harnessing massive stars is out of the question, does the microscopic realm of the quantum vacuum offer us a more practical way out?
Here's the wild thing. Negative energy isn't just some mathematical fantasy on a chalkboard. It actually exists out there in nature. See, the vacuum of space isn't truly empty. It's more like a boiling, chaotic soup of particles just constantly popping in and out of existence. And through very real phenomena, like the Casimir effect, physicists have proven that these zero-point fluctuations can actually be manipulated to create genuine negative energy. So if you were to build a rigid Casimir cavity device and place it into Earth's gravitational field, semi-classical quantum gravity shows it will experience an upward push, a real anti-gravity effect. But the scale here is, well, it's almost funny. That repulsive force is estimated to be roughly 10 to the negative 14 newtons. To put that into perspective, that is basically the weight of a single red blood cell. So is it genuine anti-gravity? Yes, absolutely. Is it useful for lifting a rocket? Not even remotely close.
But of course, theorists like F. Pinto have asked, can we scale that microscopic push-up? They've actually mapped out steps to magnify these quantum dispersion forces.
The idea is to trap polarizable atoms, zap them with external electric fields, and basically supercharge them resonantly with lasers. Theoretically, this could multiply the force enough to levitate a tiny little cluster of atoms, but sustaining that thrust for an entire macroscopic vehicle, that remains a phenomenally huge engineering nightmare.
And that leads us perfectly into part 4, the harsh, make-or-break engineering reality of all this theoretical science.
When you stack all these theories up, a clear, kind of frustrating pattern emerges. We have some brilliant, mathematically flawless ways to control gravity, but every single one of them comes with a massive make-or-break catch. Newtonian methods? You need to move entire unmovable planets. General relativity? You need the density of a dead dwarf star. Quantum physics? The forces are so impossibly small we can barely even measure them. Our current technology is just nowhere near bridging those gaps.
And the Defense Intelligence Agency? They are totally clear-eyed about this. In their reporting, they treat these concepts with total scientific respect. They definitely don't brush off the math, but they firmly, undeniably state that practical engineering implementation is just a very, very long way off. It's a pretty sobering reality check, highlighting the stark difference between theoretical physics on a blackboard and actually building hardware.
Finally, let's hit part 5, Project Green Glow, where major corporate R&D actually met fringe physics.
Back in 1997, BAE Systems actually put real money into a secretive R&D program called Project Green Glow. Led by Dr. Ron Evans, a brilliant mathematician and fluid mechanics expert, BAE carved out a legitimate space to investigate gravity control. Not as some sci-fi pipe dream, but as a genuine, potentially disruptive aerospace technology.
Evans brought together a team of hardcore, seasoned engineers to test out some pretty unconventional claims, but they did it with ruthless scientific rigor. For example, they spent time meticulously testing Evgeny Podkletenov's infamous gravity shield claims. And what did they find? A big fat zero. Null findings. They proved it absolutely didn't work. But by doing that, they successfully mapped out the dead ends and established an incredible standard of strict experimental hygiene.
You see, the real legacy of Project Green Glow wasn't that they built an anti-gravity machine, because obviously they didn't. The real achievement was building a culture where serious engineers could actually poke at audacious, kind of taboo physics without losing their scientific minds. They prioritized method over myth. They changed the conversation from "is this crazy" to "okay, what happens if we check this out really carefully?"
So no, we don't have warp drives or hovering cars sitting in our driveways today. But rigorously poking at the very edges of physics, that is exactly how our understanding of the universe keeps expanding. We already know the math for anti-gravity is fundamentally sound, so it's not really a question of if it's possible anymore, but when we will finally build the tools to pull it off. I'll leave you with this. What exactly happens to human civilization the day we finally figure out how to flick the gravity switch to off? Thanks so much for hanging out with me for this explainer, and remember to always keep questioning the limits of what's actually possible.